Good afternoon, class, and welcome to Chapter 11, Part 2. So the first thing we're going to do is practice writing another acid dissociation constant. This time we're going to do the expression for nitrous acid, which is HNO2. So again, remember that it is the products, the concentration of the products multiplied by each other divided by the concentration of the reactants. So Ka, or the acid dissociation constant, is equal to the products, which are this here and this here. So we're going to write those, H3O plus and NO2 minus, divided by the reactants. Now, don't forget that we don't do liquid water. Liquid water is not included in your equilibrium expressions. So just the HNO2. Now, before we go on, we need to raise these to the power of their coefficients. In order to do that, we need to first make sure that this equation is balanced, because if it's not balanced, then we need to balance it, and that would change those numbers there. So right now, it looks like I've got a hydrogen here and two hydrogens here for a total of 3. I've got 3 hydrogens here in the H3O plus. I've got one nitrogen, and then I've got 2 oxygens plus 1 makes 3, and 2 oxygens plus 1 makes 3. So this is balanced as is, which means that I don't need to raise any of my concentrations up to a power. So this is the Ka for nitrous acid. Okay. We have another type of equilibrium constant called Kw. This is the dissociation constant for water, W for water. Water is a special substance. It's amphoteric, meaning it could be either an acid or a base depending on the conditions it's in. Sometimes hydrogen ions, also known as protons, transfer from one water molecule to another, meaning that one water molecule would be an acid while another acts as a base. Okay, equilibrium is reached between the conjugate acid-base pair. So if you look here, this water molecule here is the acid. It is giving up the hydrogen ion to this water molecule. So we have this hydrogen ion attaching itself to this water molecule, giving us a water with 3 hydrogens and a water with only 1, right? So a water that's lost a hydrogen atom and a water that's gained 1. The water that has gained 1 has a positive charge because it got a hydrogen ion. And remember that H is H+. This guy has a negative charge because it lost an H+. Right, so now it has an overall negative charge. So this is our acid, our hydrogen ion donor. This is our base, our hydrogen ion acceptor. On the other side, going in the reverse direction, this is our acid because it would give that hydrogen ion back, this time to the hydroxide. This is our base because it would accept that hydrogen back, going in this direction. Okay? So in the equation for the dissociation of water, we have both a forward and a reverse reaction, just as shown up here. So we have water, which is acting as our base, water, which is acting as our acid, and then on the opposite side, we have our conjugate acid and our conjugate base. Okay. In pure water, the concentrations of H3O plus and OH minus at 25 degrees Celsius are both 1.0 times 10 to the negative 7 molar. So if we were to write the Kw expression for the dissociation of water, remember that we don't write the liquid water, so it would be products over reactants. What were our 2 products? Well, our 2 products were H3O plus and OH minus. Our 2 reactants were both liquid water, which don't get written in this expression. So Kw is not a fraction because there is nothing that goes underneath here. So Kw is equal to H3O plus OH minus. And again, in pure water at 25 degrees Celsius, the concentrations of both of these things are 1.0 times 10 to the negative 7 molar. We can use this information a little bit later when we have one of these concentrations and are looking for the other. So if you were to substitute in these concentrations, the 1.0 times 10 to the negative 7 and 1.0 times 10 to the negative 7, you would find that Kw at 25 degrees Celsius is 1.0 times 10 to the negative 14. Again, that's going to become important information a little bit later on. Okay, so again, the ion product constant for water, Kw, is the product of the concentrations of H3O plus and OH minus. At 25 degrees Celsius is equal to 1.0 times 10 to the negative 14. Okay, when those concentrations are equal in pure water at 25 degrees Celsius, the solution is considered neutral. It's neither acidic nor basic. When you begin to increase the concentration of the H3O plus, your solution becomes acidic. Okay? If you were instead to increase the concentration of the OH minus, your solution would be basic. So it's acidic if you increase the concentration of the H3O plus, and it is basic if you increase the concentration of the OH minus. So again, if we know the H3O plus of a solution, we can use Kw to find the OH minus. And if we know the OH minus, we can use the Kw to find the H3O plus. So that's going to become useful a little bit later on. Now, let's talk about what happens to your pure liquid if you start adding stuff to it. If you add an acid to pure water, you're going to increase the concentration of the H3O plus, meaning you're going to make the solution more acidic. If you add a base to the solution, you're going to increase the OH minus, meaning you're going to make the solution more basic. So that kind of makes sense, right? Add an acid, make the solution more acidic. Add a base, make the solution more basic. Okay? If lemon juice has an H3O plus concentration of 2.0 times 10 to the negative 3 molar, what is the OH concentration? Well, just like we've done before, we know our Kw is equal to H3O plus and OH minus. In this case, we don't know the OH minus, but we do know the Kw, which is 1.0 times 10 to the negative 14, and we do know the H3O plus since we were given it. So we can solve for the OH minus by dividing both sides by the H3O plus. So then we get that Kw divided by H3O plus is equal to the concentration of the OH minus. Kw at 25 degrees Celsius is always 1.0 times 10 to the negative 14. So 1.0 times 10 to the negative 14 divided by 2.0 times 10 to the negative 3. Now, when you're putting this in your calculator, please be sure to use the appropriate parentheses as necessary so you don't end up with the wrong answer. And this is a great problem to practice on because you can see what the answer should be. So if you type this into your calculator and you get something other than 5.0 times 10 to the negative 12 molar, you know that you've done something wrong. Okay, generally it's a problem of parentheses. Okay, so go ahead and practice on this problem, and then we're going to move on and try a couple more. All right, why do we need to know this information? Well, we need this information in order to talk about pH, which I'm sure is a term that you've heard before, but maybe you don't know what pH is really measuring. Well, pH is really measuring the concentration of the H3O plus in a solution. pH values range from 0 to 14. Values from 0 to below 7 are on the acidic end. So if your pH is from 0 right up until you butt up against 7, you're acidic. If you're above 7 and up to 14, your solution is basic. If your pH is exactly 7, you're neutral. So again, we have a pH scale, and you can see some common household items kind of on this list here. For instance, lemon juice, often used in cleaning and cooking, has a pH value of 2.2, meaning it's very acidic. Carbonated beverages like a Coca-Cola, Pepsi, root beer, any kind of carbonated beverage has a 3.0 pH value, meaning it's very acidic, which is why you might hear your dentist telling you not to drink that stuff. It's an acid, a very strong acid, in fact, and can wear away at the enamel on your teeth. Other acidic things that we come into contact often with, citrus fruits, apple juice, tomatoes tend to be on the acidic side. Coffee is acidic, although not nearly as much as, say, for example, a carbonated beverage or a piece of fruit. Bread is slightly acidic. Milk is just a little tiny bit acidic. It's close to the neutral line, right? It's a 6.4. So milk is just a little bit acidic. Laundry detergents, soaps, shampoos, cleaning agents, they tend to be on the basic side. So you can see here a picture of a laundry detergent tier, 8.0 to 9.0, dish soap, again, your soaps that you use on your body, for example, body wash, shampoos, conditioners, those kind of things tend to be a little bit on the basic side because your skin responds better to that. Seawater is basic. Global warming has caused the pH of the oceans to drop a little bit, which is not a good thing, right? Seawater should be basic. Milk of magnesia is a substance that helps treat heartburn. So since heartburn is caused by acid in the stomach, you want a base which will help neutralize that acid. So milk of magnesia, which is an old-time heartburn remedy, is very basic. Ammonia, another household cleaner, again, basic. Bleach, another household cleaner, basic. Lye, otherwise known as drain cleaner, very basic. Okay, so I just kind of want you to get a sense of what things that you encounter, whether they're acidic, basic, or neutral. Okay, so here's a few things about that pH scale. It's a logarithmic scale. Now, what does that mean? A logarithmic scale means that a change of one pH unit, so a pH from 3 to 4 or 4 to 5, corresponds to a 10-fold change in the H3O plus concentration. So a pH change of 1 does not correspond to a 1 change in the concentration of the H3O plus. It's not a 1-to-1. Instead, it's a 1 to 10. For every change in 1 unit of pH, you have a 10-fold change in H3O plus concentration. So for example, if your pH is 2.00, your concentration of H3O plus is 0.01 molar. If your pH is 3.0, your concentration is 0.001 molar. And if it's 4.0, it's 0.0001 molar. So you can see that each time we have a 10-fold increase. So here our 1 is in the hundredths place, then it's in the thousandths place, and then here, tens, hundreds, thousands, 10,000s. So clearly you can see that we have a 10-fold change every time we have a change in pH of 1. Okay. Let's do some calculations here, because I know that doing practice problems is important. Aspirin, which is a pretty common household item. I'm sure if you go look in your cabinets now, you have some. Aspirin is also known as acetylsalicylic acid, and it was the first non-steroidal anti-inflammatory drug used to alleviate pain and fever. If you were to take aspirin and break it up and create a solution out of it, the H3O plus concentration would be 1.7 times 10 to the negative 3 molar. We want to know what is the pH of the solution. So our pH equation is that pH is equal to negative log the concentration of the H3O plus. So the pH of our aspirin solution is equal to negative log 1.7 times 10 to the negative 3 molar. Okay, when typing this into your calculator, if you're using a Texas Instrument, one of the newer models, you should be able to type in the negative sign, then hit the log button, okay, and then type in your number in scientific notation. So 1.7 times 10 to the negative 3, okay, should give you a pH of 2.77. If you're using an older model, some of the older models, you can't type in the negative sign first, right? You have to type in the log, the number, and then hit the negative sign before you hit enter. If you run into trouble using your calculator, please don't hesitate to let me know. If you take a picture of the calculator, maybe I can help you figure out how to use it, because all calculators are different. And again, if you're using one of the newer Texas Instruments models, it's really easy. Hit the negative key, the log key, which on my Texas Instrument is on the left-hand side, 6 keys down. Okay, so hit the negative key, the log key, and then type in your number in scientific notation and parentheses and hit enter. Okay, let's try another one. Again, pH is equal to negative log the concentration of the H3O plus, which is 4.0 times 10 to the negative 5. So go ahead, pause the video here, type this in your calculator and see what you get. Okay, I got 4.35. My pH is equal to 4.35. Okay, is that acidic or basic? Hey, a pH, anything below 7 is acidic, so both of these solutions are acidic. This top one we just calculated is acidic. This bottom one that we just calculated are acidic. Okay, what if you're given the pH of a solution and you want to know the opposite? You want to know the concentration of the H3O plus. So for undoing pH, what you really want to do is undo the log. I know some of you haven't taken math in a while, so let me just explain this. To undo the log, you're going to raise your number to the power of 10. So you're going to have 10 to the negative whatever your pH is. Okay? So to undo that log, to find the concentration of the H3O plus, you're going to do 10 and then raise that to the power of the negative pH. So generally speaking, you're looking for the 10 to the X button, which on my calculator is right above the log button. So if you look at the log button, you see written right above it on mine, 10 to the X in blue, which on my calculator means hit the second key and then the log key. So it's the exact same key. The only difference is I'm hitting the second key first. Okay, so let's try one. All right, we're going to determine the H3O plus for a solution that has a pH of 3.42. So again, remember to determine the concentration of the H3O plus, okay, we're going to do 10 to the negative 3.42. Okay, when I type this into my calculator, I get 3.80 times 10 to the negative 4 as my concentration for my H3O plus. Again, if you're running into trouble with your calculator using an older model, or maybe you're just having a hard time with it, please don't hesitate to send me an email. I'll be happy to talk to you about how to use your calculator. Okay. Acids react with metals to produce hydrogen gas and the salt of the metal. So if you were to take a metal like potassium and dip it in hydrochloric acid, you would get a salt, which is KCl. Not a salt like I beat you up, salt like the food. Only it's not sodium chloride. In this case, it's potassium chloride. And hydrogen gas. So if you've ever had a chance to do this in a high school lab maybe or in another place, when you take an acid in a beaker and you drop metal in it, you get a gas that forms. So you get all these little bubbles that come up. So when we do in-person labs for this class, we take a balloon and we tie a balloon over the surface of our beaker. And when you drop the metal in to the acid, the balloon blows up. So the balloon gets really big from the hydrogen gas. Unfortunately, you guys don't quite get that experience, but still, hopefully you can picture it in your head. Okay, you get a salt and hydrogen gas. We also have another type of acid-base reaction called a neutralization reaction. This happens when you have an acid and a base, and instead of a salt and hydrogen gas, you get a salt and water. Okay, the salt formed is the anion from the acid, right? In this case, chlorine. And the cation from the base, in this case, sodium. So the sodium and the chlorine pair up, and they make sodium chloride, and what's left is OH and H. HOH is H2O, which is water. Okay? So if we were to write the strong acid and strong base as ions, because remember that strong acids and strong bases dissociate into ions 100% in water, you would get H plus and Cl minus, and then you would get Na plus and OH minus. Okay, those are my strong acid and strong base as ions. We can see then that the H plus is not going to react with the Na because they're both positively charged. Two positively charged things are going to repel each other. Instead, the H plus is going to react with the OH. So again, we have HOH, which is water. That leaves Na plus and Cl minus, which would form NaCl. If you look at your solubility rules from a couple of chapters ago, you will hopefully remember that anything in group 1 is always soluble, meaning it will dissociate in water. And so when you're done with all of this, you will still have sodium ions and hydroxide ions in water. Okay? So the overall reaction, right, if you cross out your spectators, is going to be your H plus OH minus gives H2O. Okay, this is a little bit of review as far as spectators crossing out ions, that sort of thing. Hopefully that's something that's ringing a bell with you. Okay, and finally, one of the last things that we're going to talk about is the titration of an acid. So this is what happens if you have an acid of a concentration that you don't know. So say you have an acid, and you know it's an acid, but you don't know the concentration of the acid. What you can do is put this in a flask with something called an indicator. An indicator is something that changes color when its pH changes. So typically we use an indicator that's clear at acidic values and turns a color when you hit neutral. Okay, so you add an indicator in here that's going to change color when your solution becomes neutral. Then what you do is you take a base, and you take a base that you know the concentration of. So you take a strong base in here, typically sodium hydroxide or some other strong base, whose concentration you do know. And you add that base drop by drop into your acid solution until your acid solution is no longer acidic. Because remember what happens when you have an acid and a base mixed together from the previous slide. You have a neutralization reaction, meaning you're going to produce water and your salt, neither of which have a pH above 7. So both water and salt in their pure forms should have a pH of right around 7. They're neutral. So if you know the concentration of your base and you know how much base you had to put in here to make this neutral, and you know the starting amount of your acid, you can find the concentration of the acid. Well, how do we do that? Well, that's what I'm going to show you right now. So we have an HCl solution. We don't know the molarity of it. What is the molarity of an HCl solution? So again, we're looking for the concentration of the hydrochloric acid. If 18.5 milliliters of a 0.225 molar NaOH is required to neutralize it. So we know the concentration of the NaOH. It is 0.225 molar. And we know how much of it. We needed 18.5 milliliters in order to do this. Now, we don't know the concentration of our acid. This is for our base. We are trying to find the concentration for our acid. But we do know how much acid we originally put in the beaker. In this case, we put in 0.0100 liters of our acid. So what do we know here? We know the concentration of the base, we know the volume of the base, and we know the volume of the acid. Step 1 in any acid-base titration reaction is always to ensure that you have a balanced reaction. Okay, a balanced reaction. So we have hydrochloric acid plus sodium hydroxide gives sodium chloride and H2O. I have one hydrogen here and one hydrogen here, so that's two hydrogens. On the right-hand side, I have two hydrogens. I have one chlorine, one chlorine. I have one sodium, one sodium. One oxygen, one oxygen. So my equation is balanced. Again, please remember, it's vitally important to have a balanced equation because we are going to have to do a mole-mole ratio. If you don't have a balanced equation, your mole-mole ratio will be off. So step 1, balance reaction. Step 2 is going to be to find the number of moles of base. Okay, you have the concentration of the base and the volume. You are going to find the number of moles. So we have 0.01 0.225 capital M, which means molarity, which hopefully you remember means moles per liter. Moles per liter. Now, we don't have an entire liter of our base. Instead, we have 18.5 milliliters. Since our molarity is in moles per liter, we need to convert our milliliters into liters, which means dividing by 1,000. So we have 0.0185 liters of our base. Since liters are on the bottom, we want to multiply by 0.0185 liters to cancel the liters out. This will leave us with moles. So 0.225 times 0.0185 gives us 0.00416 moles of base. Okay, this is moles of base. Now, according to our balanced chemical equation, for every mole of base, we need 1 mole of acid. For every mole of base, we need 1 mole of acid. That's our mole-mole ratio. So, for every 1 mole NaOH, we need 1 mole HCl. Since this is a 1-to-1 relationship, that means we have 0.00416 moles of our acid. Okay, how do we find the concentration of something? The concentration is measured in molarity, which is moles per liter. We know the moles of acid, and we know the liters of acid since it was given to us in the problem. That's what we put in our beaker. We put 0.0100 liters of acid. So to find the concentration of the acid, 0.00416 divided by 0.0100 gives us a concentration of 0.416 molar for my hydrochloric acid. Okay, let's try one more. Example 12 says, what is the molarity of an HCl solution if 25.5 milliliters of sodium hydroxide is required to neutralize 0.0250 liters of HCl? So again, what do we have? We have the concentration of the base, 0.438 molar. We have the volume of the base, 25.5 liters. We also have the volume, this is all for our base here. We also have the volume of our acid, 0.0250 liters of our hydrochloric acid. So I'd like you to pause the video right here and attempt to work this out on your own. Please go ahead and do that now. Okay, welcome back. So here's what we're going to do. We're going to do just like we did in the previous equation. We're going to make sure we have a balanced chemical equation, which is the same stuff from the previous one, HCl and NaOH. So we have a balanced chemical equation. Step 2 is going to be to convert the base into moles. So we have molarity, which is moles per liter. So we have 0.0438 moles of base per liter of base. Okay. But we don't have a whole liter of our base. We have 25.5. And by the way, that should be ml, not liters. We have 25.5 milliliters. Okay? If we convert that into liters, right, we would divide by 1,000. And so that would be 0.025 liters. 255 liters. Now my liters cancel, leaving me with moles. So 0.438 times 0.0255 tells me I have 0.0112 moles of base. Next step, mole-mole ratio. Looking at the above equation, right, our balanced equation up here, this is a 1-to-1 relationship. So for every 1 mole of NaOH, we have 1 mole of HCl. Okay, that means that we have 0.0112 moles of acid. Molarity, which is concentration, is moles divided by liters. We have 0.0250 liters, and we have 0.0112 moles. So 0.0112 divided by 0.0250 liters should tell us the concentration of our acid. And I get 0.447, 0.447 molar HCl. Okay. Again, remember, the steps for solving one of these is make sure you have a balanced equation, convert your base from molarity and milliliters into moles, use your mole-mole ratio, and then solve for your concentration of your acid using the volume that you're given and the moles that you found. Okay, finally, the last thing that we're going to talk about are buffer solutions. So what buffer solutions do is they help maintain the pH by neutralizing small amounts of added acid or base. So when you have a buffer solution and you add a little bit of acid or a little bit of base to it, you don't change the pH. Okay? In order to do this, you have to have an acid present to react with any OH added and a base present to react with any H3O+. So basically you need to have both, each one to neutralize the opposite. When you add an acid or a base, the pH changes drastically if you don't have a buffer solution. In a buffer solution, though, the pH is maintained. Okay? So buffers work because they resist changes in pH from the addition of an acid or a base. In the body, they absorb H3O+ or OH- from the foods that we eat and cellular processes. This is what helps us stay alive. Okay. Buffers are really important to the proper functioning of cells. And in fact, your body has buffers, including your blood. Okay. They maintain a pH close to 7.4 in blood, which is just tiny bit basic. Remember that 7.0 is neutral. Anything above 7.0 is basic. So your blood is about 7.4. Okay. A change in the pH of the blood would affect the uptake of oxygen in cellular processes, meaning it would kill you, right? If you change the pH in your blood too much, it will kill you. So this is really important to have a buffer to help maintain the neutrality of your blood. Okay? A buffer solution contains a combination of acid-base conjugate pairs, a weak acid, and a salt of its conjugate base. So an example of this would be acetic acid, C2H3O2-, okay? Or I'm sorry, HC2H3O2-, that's the acid, acetic acid, and this is its conjugate base where it's given off the hydrogen ion already. Okay, and it would have equal concentrations of the weak acid and its salt. So both the concentration of these things would be equal in order to create a buffer. Thus concludes Chapter 11, Part 2, as well as the semester. I hope you've enjoyed yourself, and I'm looking forward to seeing all of you in Chem 1152. Enjoy your break.